In this lecture, we will learn how Jacobians arise, what are their applications, what is Jacobian matrix. The most frequent application of Jacobians arise during the variable transformation. When you do some integral, you integrate, you usually convert or transform a variable into another. So let us take an example before actually going to understand what Jacobian is. So let us have an integral. Let we have to integrate I is equal to e to the power square root of t dt. So the most obvious thing that you do is that you take a transformation t is equal to x square, which in return yields dt is equal to 2x dx. So obviously you substitute t is equal to x square and dt is equal to x dx so that the integral is converted into e to the power x and 2x dx. You take these two common and integrate by parts, so the integral become x minus 1 e to the power x, and finally you take the substitution back so that it becomes 2 into square root of plus minus square root of t. It depends upon the, actually this is indefinite integrals. When there is definite integral, the limits are specified and the values are plus minus square root t depends on the limit, if it is in positive side of 0 or negative side. So this minus 1 e to the power root t. So why I have taken this example? The transformation t is equal to x square. When you did this, when you took t is equal to x square, you did not directly put dt is equal to dx. You put dt is equal to 2x dx. So what is this? When you take a transformation of the type x is equal to fy, then you put dx is equal to derivative of f with respect to y and dy. This f dash y is known as Jacobian of transformation. Jacobian of transformation. Which transformation? Transformation of x into y. But usually, while using the one variable functions, dealing with the functions of one variable, the name is not uh, of trend. This is not of trend. So you do not know what the Jacobian of transformation is, and you generally take the transformation, go on to solve the integral or do your purpose. But if we deal with the functions of two variables or more variables, then you cannot directly write the same thing. For example, you take x is equal to f of uv and y is equal to some g of uv, then you cannot directly write dx dy is equal to du dv. This will be wrong. So how to deal with this type of problems and where does this arise? These of the problems of these types arise during the integration of surface or volume, or you can say during surface integral or volume integrals or multiple integrals. So if you have integration and n variables n integrals, then the problem may arise. So why do we do this? Usually we take the transformation in order to simplify the process of solution. So now let us see what the Jacobian are and how the Jacobian arise. Suppose some mathematical process involve two independent variables. Let or simply you can say involves two variables u and v, and let us take the transformation of u and v by some means into x and y. So let u be transformed into x and y, and v be transformed into x and y by some means. What does this mean? When you write z is equal to some function of x and y, what does this represent? This represent a surface. This represent a surface. So in fact, u is a function of x and y. This represent a surface, and v is a function of x and y. This also represent a surface. So in general, we transform Cartesian coordinate into some other coordinate, uv plane. We can say uv plane. So what do we do actually? So because we know that we have taken u as a function of x and y, so when x changes, u changes. When y changes, u changes. So suppose we change x by a small amount, delta x. Let x is change to x plus delta x. What will happen? U will also change, and I am not talking of y this time, so y has been kept constant. So keeping y constant, just change x. So x is changed from x to x plus delta x, means there is a change of delta x in x. So there must be a corresponding change in u. So corresponding change in u is delta u. When you change x by delta x, there is a corresponding change in u, and that is represented by delta u. So what is the rate of change? The rate of change of u is delta u by delta x. And in the limiting process, this is denoted as del u by del x as a partial derivative, and you know well what del u by del x is. If you do not know, then you go back, first read what partial derivative are, then come back to this video again. So the rate of change of u is del u by del x, and corresponding to a change delta x in x, what will be the total change of u? Total change in u due to a change delta x in x is equal to del u by del x delta x. So this is the change in u due to change in x. Similarly, if we change y, there will be a change in u, and that if we denote change in y by delta y, the change in u will be delta u. So that will be del u by del y delta y. So similarly, if y is changed by delta y, the change, the corresponding change in u is del u by del y delta y. So let us take these changes as a vector entity. So what is vector entity? Means u is changing in the direction, some direction, and there suppose this is x direction, this is y direction, and this is this is u direction. So we take I unit vector in the direction of x, and j unit vector in the direction of y, and k unit vector in the direction of u. So the changes in u are total changes in u due to change in x and change in y. Total change in u due to changes in x and y this is equal to del u by del x delta x I direction in I direction plus del u by del y delta y in j direction. So in limiting position we can also say this in limiting position. What is limiting position? Limiting position means when delta x delta y tends to 0. So in limiting position total change, and if we denote this total change by du, so the total change du vector, this is equal to I del u by del x dx plus j del u by del y dy. So this is change in u and we denote it by du. Similarly we find change in v, and the vectorial change is denoted as dv is equal to I del v by del x dx plus j del v by del y dy. So what is happening and why we have considered du and dv? So during double integration, because I have taken only a function of two variables, a transformation of two variables into two variables, so it concerns with the double integration. When you perform double integration, something of the type fxy dx dy, and you change variables x and y into some other variable, or say just take what we have taken here du dv, integral is of the form f of ub du dv, and you take the transformation u is equal to x function of xy and v is function of xy, then you have to transform everything here. Limits will be transformed, limits will be transformed, this f will be transformed, so there will be some other function phi of x and y, and du dv will be transformed into something dx and dy. And I have already told you that when you taken t is equal to x square, you did not write dt is equal to dx. So obviously here also you will not write du dv is equal to dx dy. So there will be some factor, this factor may be constant and may be function also. So this factor, we have to find out what this factor is. So if we have to transform the variable during the double integral process, we will have to find out how du dv will be transformed into dx dy. So what is du dv? Du dv is an small area. So a small area in UV plane will be transformed into a small area in XY plane, but the small area may be changed in shape, size and orientation. So how will find that thing? So how will du? So area small, how du dv small area du dv in a plane. So area in UV, or we can say it elementary area. So elementary area du dv. What is this? This is magnitude or vector product du dv. This. So we can find the vector product. So let us find this. So du dv is equal to du dv, and this is equal to I del u by del x dx plus j del u by del y dy. This and the cross product with I del u del v by del x dx plus j del u by del vy del y dy. this is cross product. And as a thumb rule, I should remind you that if you take I, J, K, write it in circular position. So I cross J is K, J cross K is I, and K cross I is J, and I cross I, J cross J, K cross K are 0. And in reverse direction means clockwise direction, K cross J is minus I, J cross I is minus K, I cross K is minus J. So we will use it here. So use the same technique to find this. I cross I will become 0 and I cross J will be K. So this is K, del U by del X, del V by del Y, and dx dy will be there. So J cross I is minus K, minus K, del U by del Y, del V by del X, and dx dy is common to both, dx dy. So we have transformed this and the magnitude of this cross product. So what is magnitude? Du dv is equal to del u by del x, del v by del x, and del u by del y, del v by del x, del v by del y, this determinant into dx dy. You can check this determinant opens as del u by del x, del v by del y, which is the first term, minus del u by del y, del v by del x. So we have transformed the small area of uv plane into xy plane. So if we define j u v x y as this Jacobian del u by del x, del u by del y, del v by del x, del v by del y, then we can write du dv is equal to j dx dy, and this j is called Jacobian of transformation. Jacobian of transformation. So this is Jacobian of transformation of uv with respect to xy, means when uv is transformed into xy, this Jacobian arises and the elementary area du dv is converted or transformed into j times dx dy. So before going to the third or higher dimension analysis of the same thing, let us take an example. Find the Jacobian of transformation j x y r theta if x and y are transformed into x is equal to r cos theta, y is equal to r sin theta, means x and y are transformed into r and theta. Cartesian coordinate is transformed into cylindrical coordinate. So what will we do? Jacobian. Jacobian is, so how do we write this Jacobian? Take the first function and find its partial derivative with all the variables. What are the variables? R and theta. So del x by del r, del x by del theta. Now take the second function y and its partial derivative, del y by del r, del y by del theta. This will come out cos theta minus r sin theta, and sin theta r cos theta. You can simplify this, r cos square theta plus sin square theta is equal to R. So now we will denote a common notation of the Jacobians. Jacobian of transformation of uv into xy is usually denoted by this. This is denoted J U V X Y. So in sometimes instead of writing J U V X Y, we write this notation del U V by del X Y and read it as Jacobian of transformation of U V with respect to X Y. So what we have obtained is Jacobian of transformation of X Y with respect to R theta is equal to R. So if we take a double integral fxy dx dy and transform the coordinates into polar coordinates, cylindrical polar coordinate r theta, then we will obtain integral something phi r and theta r dr d theta. Why? Because dx dy will be transformed into dx dy will be transformed into j times dr d theta, and we have obtained j as r. So this is equal to r dr d theta. So we will write this x in as r cos theta, y as r sin theta, and dx by dx into dy, this will be written in polar coordinate as r dr d theta. So now we try to understand how this same thing arises in three dimension. So let us transform three variables u v w into x y z by means of some transformation, means functional relation u v. So we took some functional relation to transform u, v and w into x, y and z. So by this similar approach we have developed in the last few minutes to derive the Jacobian of transformation for two variables. We will use when we change x, you will change; when we change y, you will change; when we change z, you will change. So what will be the Jacobian, what will be the vectorial change in u? So vectorial change in u due to change in x, y, z, this will be du, because we have already developed the tool. So we will have del u by del x dx, and this is I component, means this change will occur in x direction, and then j component del u by del y dy plus k component del u by del z dz. Similarly, we will have dv is equal to I del u del v by del x dx plus j del v by del y dy plus k del v by del z dz, and finally dw will be I del w by del x dx plus j del w by del y dy plus k del w by del z dz. So what will be correspondence of the two variable into the three variable? So in two variable system, means two dimensional plane, we transform elementary area into elementary area, and in three dimensional system we transform elementary volume into elementary volume. So what will be elementary volume? So elementary volume will be elementary volume is calculated as du, dv, dw. This is equal to du dot dv cross dw. This is how we calculate elementary volume in simple vector mathematics. So you have already used vectors. If you have not used, then please go back again and read about the vectors. I am not much intended to involve vector calculus, but you must know little about the vectors. So when using vectors, the volume is calculated in this form. This is called scalar triple product, and even we do not need to write this magnitude because it is already scalar. So du dv dw volume is calculated as scalar triple product of three vectors. So this elementary volume will be calculated as this. So now in order to find the Jacobian relation, we will substitute du dv dw from these expressions into this. So what will this be? So first we will calculate dv cross dw. So you know we have already calculated this, but here this will be a little different because we have taken a third dimension k, I, j and k. So this will be, so this will be I, j and k, writing a little distant. So this will be del v by del x dx, del v by del y dy, del v by del z dz. Or it is better to write in shorthand notations. So what will be shorthand notation? It is if you are comfortable you can write. If you are not comfortable, then you can write the usual notation. This is Vx means del V by del x, this is Vy del V by del y, and this is Vz means del V by del z. So this Wx dx, Wy dy, and Wz dz. So let us open this. This will become I Vy Wz dy dz minus Vzwy Vzwy dy dz and we will arrive with two similar expressions with j and k. This, so you can calculate this. This is your homework. So I am going to write this in sigma notation. What is sigma notation? Means one expression will be written here and two other will follow similarly. So this will be Vywz minus Vzwy and dy dz. What does it mean? One expression with I have written here, and with sigma means with j and with k, two other expressions will be some here. You will say some the expression means this I this and j this and k this. You will open as your homework. So this we have calculated du dv cross dw. Now we have to calculate du dot dv cross dw. So this is but obvious. We know du is equal to I ux dx plus j uy dy plus k uz dz. We know it. So again I am writing this in sigma notation. So this is equal to I ux dx ux dx. So this is sigma notation for d vector du, and then this sigma notation for this I Vy wz minus Vz wy dy dz. So this is how you will take the dot product. And now let us summarize this. So this will come out of the type because you know dot product. So this item will get product with I, and I dot j I dot k will get 0. So next term here will be j times something, means j ui dy. So that will get product with j term, corresponding j term in this sigma, and j dot I, j dot k, that will become 0. Similarly, so finally you will get terms, first term I with I will yield ux dx Vy Wz minus Vz Wy dy dz, and finally I am writing this sigma, and that means two more terms will occur of this type. So what is this? So let us take this dx finally at the right side. So we have this is equal to, and this is du dv dw. This is sigma ux Vy Wz minus Vz Wy dx dy dz. So you can observe that we will obtain two more terms. So now let us expand all the terms. So we have obtained du dv dw. This is equal to ux Vy Wz minus Vz Wy dx dy dz plus two more terms, and finally you can write this as ux uy uw. I hope that you will write two more terms and will observe this vx vy vw wx wy vx, this z and wz, this into dx dy dz. So we have transformed du dv dw. This is elementary volume in uvw plane, and this is elementary volume, corresponding elementary volume in dx dy dz plane, xyz plane. So this is how we transform. Again we name this determinant as j. So we have du dv dw. This is equal to j dx dy dz. So usually the same thing follow in higher dimensions also, and there is a custom to write this as du dv dw. This is equal to j times dx dy dz, and because this notation actually help to write the higher dimension relation. So what the higher dimension relation will be? So if you and finally I am summarizing here, du dv dv, this is just a vector notation, and when we take product of these small differentials, we get du dv dw is equal to j times this, and j is defined as this in general. So let us first define j for n cross n, or n variable to n variable transformation. So if you transform u1 u2 un into x1 x2 xn, then Jacobian of transformation will be written as: take first function, write down all its first order partial derivative with respect to x1 x2 xn. So u1 x1 means del u by del u1 by del x1. So let us write for the clarity in the same form. So del u1 by del x1, then del u1 by del x2, then del u1 by del x3, and so on, del u1 by del xn. Means all the first order derivative of u1 are written in a row, and then take u2, then del u2, then write all its first order partial derivative in second row, del u2 by del x2, and this way del u2 by del xn, and finally del un by del x n, del x1, del un by del x2, del un by del xn. This is the Jacobian of transformation of n variables. So I don't hope that you will need multiple variable of nth order or n variable. So you will only need transformations in two or three variables. So two or three variable during integration process means you will need variable of transformation of two variables during double integration, and you will need transformation of three variables during triple integration. But there is an other thing also. When this Jacobian is zero, these functions are functionally dependent, means they have some relation. When this Jacobian is non-zero, these functions are not functionally dependent, means they do not form a functional relation. So this is also an use of the Jacobian of transformation. Now let us take another question to see how we use the Jacobians during integration process. Let us take an integral of the form minus infinity to infinity e to the power minus x squared dx, and I hope it is not easy to evaluate this integral in Cartesian coordinate, because integration of e to the power minus square x square is not very easy, and particularly I never tried to integrate this directly, and if you can try. So let us take the evaluation of this system, this integral, with the Jacobian of transformation, means transformation of variables. So let us denote I is equal to minus infinity to infinity e to the power minus x squared dx, so that I square can be written as I square can be written as I square is equal to minus infinity to infinity e to the power minus x square dx into minus infinity to infinity e to the power minus y square dy. This can be written as minus infinity to infinity minus infinity to infinity as a combined integral, because the limits are independent of variable, constant limits are there, so we can directly write this as e to the power minus x square plus y square dx dy. And because the function integrand is symmetric in x and y, means you can replace x with minus x, this will not change the function. You can replace y with minus y, this also will not change the function. So due to symmetry, we can evaluate this integral in the first quadrant only. So we will take 4 times 0 to infinity 0 to infinity e to the power minus x square plus y square dx dy. So now we will take a transformation in cylindrical polar coordinate. So let x is equal to r cos theta, y is equal to r sin theta. So r will vary from 0 to infinity, and theta will vary from 0 to pi by 2. Why 0 to pi by 2? Because we have converted the integral into first quadrant only. So in first quadrant, theta is 0 to pi by 2. And as we have already seen in a previous example, that dx dy will be equal to Jacobian times dr d theta, and we have obtained the Jacobian of xy with respect to r theta for this transformation, and that is r. So this will be r dr d theta. So what we get is I square is equal to 4 times 0 to infinity 0 to pi by 2. Obviously 0 to infinity limits stands for r, and 0 to pi by 2 for theta. So e to the power minus r square r dr d theta. Because limits are constant, so we can evaluate independently 0 to pi by 2 d theta and 0 to infinity r e to the power minus r square dr. So you know that first integral is directly equal to pi by 2, and so this is equal to 4 pi by 2 0 to infinity r e to the power minus r square dr. Now this will become, this 2 will cancel 4 into 2 times, so 2r dr, and this we can write is pi 0 to infinity 2r e to the power minus r square dr. And now you can integrate it easily by taking r square is equal to t. So 2r dr will become dt and limits will not change. So this will become e to the power minus r square by minus 1 0 to infinity, and this is pi. So I square is pi. So what is I? I is square root of pi. So we have obtained minus infinity to infinity e to the power minus x square dx. This is equal to 2 times this is equal to minus infinity to infinity e to the power minus x square dx. This is equal to 2 times 0 to infinity e to the power minus x square dx. Or directly I is root pi, so why do we write in 2 times 0 to infinity? This is I minus infinity to infinity e to the power minus x square dx. This is I, so this is equal to square root of pi. So this is what we obtained with the use of Jacobian of transformation. Now to avoid the length of video, I am winding this video here. And if you want to see more applications and more usage of Jacobians, I will make subsequent sequential videos. There are a lot of applications of Jacobians. This is not limited to integration only. So please be in contact for future videos, and you can like and subscribe the channel. Thank you.